might just need like an extra night to work on this.
Yeah. But yeah, then I'm doing this stuff, which is pretty straightforward. I just kind of forgot about it. So
No, yeah, exactly. Well, that helps with number one at least.
yeah.
All right, is the School of Mines connected?
Yep, I can hear you.
All right, good. So, and don't forget to turn in your homework. So far, I think I only have one. We'll do that by the end of the day. Hopefully it wasn't too rough. And yeah, there'll be a second homework soon, maybe later today, but I'll send it out. Or does it, do you get an email, by the way, if I update the D2L page?
Do we? I don't know.
No. Okay, well anyway, I'll send an email about it if I do post that. So by the way, I wanted to highlight, so this is just a note about scalar fields, about real scalar fields, that I glossed over. So someone asked about this, so I wanted to make this more clear. So right, I was claiming, right, when we do this Fourier expansion, that the Fourier expansion for a real scalar requires that you impose sort of a funny condition when you impose. So this is the coefficient in front of the EDIX thing, right? This thing is 5 minus k. So you need to impose that if it's real. This is basically an artifact of using this Fourier expansion that has a, complex number in it, but we're applying this to a real field. So you could see that. So I just wanted to explain where that condition comes from. But right, a way to see that is to look at what's that Fourier expansion look like schematically. So it's d3k, phi k, d to the I kx. And the conjugate one, b d3k phi star k, e to the minus I kx, right? So that's nothing controversial, just writing down the normal Fourier expansion and doing the complex conjugate of 1. So right, we want to impose, what does real scalar field mean? It means phi equals phi star. So right, so I'm going to be setting these two equations equal. So if I'm looking over on the right-hand side at that expansion, again, right, I should really think of this as being k and k prime or something, because these are two dummy indices. They're not the same thing. But let's look at the exponential, right? If I want these, phi and phi star to be the same, I'm going to need, right, that they're the same in all values of k, right? I mean, I need the exponentials to match, right? The only way that's going to happen is if k prime is equal to minus k, right? So the only hope is k prime is minus k. So, and that's it. That will do it, right? So the exponentials will be the same, and now we just require this condition, right? So that's how we would get that. It's 5 k minus. So that's why, it came up when we were checking some commutator. We had to impose that. And if the thing is complex, you don't have that condition. And there's actually more degrees of freedom as a result of that. This really simplifies things. I mean, right, we talked about it a little bit when we were looking at the equations of motion and talking about Noether's theorem. But for a complex field, you can sort of think of there as being twice as many degrees of freedom as there are for a real, right? We can think of phi and phi star as separate things. And we'll come back to that. Because, right, so far, our first step in doing a quantization of the field, that was only done for a real scalar field so far. So we'll see what happens with a complex field a little bit later. Maybe actually for our homework problem. Okay, were there any questions about this? Okay, so let me start now talking about, we're still mostly doing some formalism stuff. And I think starting next week, don't forget that there's no class on Monday because of Labor Day, so we'll only have one class next week on Wednesday. But starting next week, the plan is to start with this review or introduction to doing complex contour integrals, which we'll use when we study the propagator for scalar fields. So just so you know where we're going. So we're going to do a little more formalism right now. But I want to start by asking a question, right, to motivate what we're going to do, which is, could we ruin Lorentz invariance when we did our quantization? So we'll see it's often hard to find a good picture, a good way to do quantum field theory that's obviously quantum mechanical and obviously Lorentz invariant at the same time. So the reason I'm asking this question, if we ruin Lorentz invariance, is because let's look at our CCR, our canonical commutation relations. Right, these were phi x, phi y is I delta function, and the others are 0, phi pi, pi pi, for whatever positions are, right? This is what we found. The reason, so why might this make me wonder about Lorentz invariance? Well, because it depends on 3 vectors only, right? There's nothing about time here. But relativity and Lorentz invariance and all that tells me time and space are all mixed up. So how can am I doing something weird here? Right? These are time-independent relationships. Time-independent, but space, right? That seems a little weird. It seems like maybe there's some tension, right? So in this way, we did quantization. There's some tension with making it obviously quantum mechanical, being close to non-commutation relations, but it's less obvious that we preserve Lorentz invariance. Maybe we accidentally broke something. And there's a way to check. And so the other part of formalism that we're going to start to look at now, we haven't looked at yet, is remember in quantum mechanics we had these 2 different pictures for how to look at time evolution. We could call it an active transformation, where we look at how the vector changes with time. Or, since the only thing that's observable are observables, we look at things like their expectation values. And when we calculate those things, if we want, we can forget about the vectors as transforming in time and just think about the operators changing in time, the observable itself. So secretly what we did here was use, so we implicitly, I didn't stress it, implicitly took the Schrodinger picture So now we're going to look at the Heisenberg picture. Let me remind you what that means to. So this is sort of motivating looking in more detail at the Klein-Gordon field in space-time. So this is sort of familiar, right? Stuff about Schrödinger picture and Heisenberg picture, and active versus passive transformation. So let me just remind you too, in case it's not super fresh. So in back in the good old days, the non-relativistic quantum mechanics, right? Crucial quantities are things like expectation value, as an example. That's the most helpful way to look at the difference between the Schrödinger and also then Heisenberg picture. So if we look at some expectation value, so this is now really old stuff, right? So we're looking at the expectation value of some operator, A. The way to define it, right, was I look at the inner product of my state psi sandwiched around that same operator, right? So this is why it's up to us who we think of as having time dependence, because it depends on two things, the state and the operator, right? So now if I want to look at how does that thing time evolve, right? There are two pictures, right? There's one where I look at psi having all the action, and A is just along for the ride. This is called the Schrödinger picture. Picture. People call it picture, I guess, because there's not some other good name for it. It's just a way of defining the transformation. Or I could say, no, the states are forever fixed, right, and all the operators change with time. And that's called the Heisenberg picture. There's, in our way of thinking about what this picture idea means, right, there's actually an infinite number of pictures if we want, because I could choose both of them to have a little bit of the time dependence if we wanted. There's something called the interaction picture, which is basically they both have half of the time dependence. And people use that sometimes in field theory too, but we're not going to do that right now. And you could pick your own where only 30% of the time dependence goes into the states or something if you want, but that's probably never going to be useful. But just to emphasize, right, that there's nothing, these are like the extremes. Right. So what that means formally, right, in terms of how we look at time dependence, it would be so for the wave function or the state vector in the Schrödinger picture, how that changes in time is right with this unitary time evolution. So that's for Schrödinger. And the way we think of time evolution for the operator then will be that, right, for this to give us the same expectation value, right? The expectation value at the end of the day has no dependence on what your picture is, right? Your picture is how you're thinking about it in your head. So for this to give me the same expectation value, right? In the Schrödinger picture, I'll have a U appear here, but also a U dagger. So that means in the Heisenberg picture, A has better evolved the same way. It'll be sandwiched around a U dagger and a U, right? Right, so that's in the Heisenberg picture. Okay? So it's just two different ways of thinking about time dependence. So you fix to one and then solve the problem all that way. I mean, only switch between pictures if you really have a good reason for doing it. Got it. So now we're going to go to the Heisenberg picture in field theory to look at, make sure we didn't do something weird when we quantize. So for quantum field theory in the Heisenberg picture, now the field, which before with our canonical commutation relationship was time independent, now the field, which is our operator, so something like A, now this field can depend on time. So the way we should define it, right, would be with the e to the I ht by x to the minus I. So remember to, right, we found a nice general result from non-relativistic quantum mechanics was all the time dependence was e to the I ht. So just using all the stuff we knew from before, we should be able to write the the Heisenberg picture time-dependent field in this way, and the same for pi. And the time dependence of any operator I don't remember if we actually used this, so this is unfamiliar. We can talk about where this comes from. For any observable or operator, I would get the time dependence in the Heisenberg picture from its commutator. Is this familiar? Yes? Okay, so let's check that now. Let's now find what this time dependence really looks like, right? This would allow us to calculate, for example, d phi dt, right? Something we haven't talked about yet. Those will all lead up to eventually also thinking about propagators in quantum field theory. That's why we unfortunately have to do this small detour to talk about complex contour integrals, but they're really essential for propagators. Okay, so far, we're just rewriting all of our field theory stuff now in this different picture, in the Heisenberg picture. So now we can look at time evolution. Things like d phi dt. Right, just using the Heisenberg equation of motion. So let's do that. Start writing it down. So we'll have I dt phi xt. And we'll want to do the commutator of the full Hamiltonian, right? So for a massive real scalar field, that's a big equation, right? With a dummy variable integral over it. So I'll have a fairly big commutator to evaluate. But will be made doable with our commutation relations. So I'll call the dummy variable y. So and remember what the Hamiltonian density looks like. So we have something pi squared, something with a 1/2 and d phi, which is now these y variables, d phi squared and a 1/2 m squared phi squared. phi is yt. This is a closed bracket. Is that clear for school minds? Can you read that equation?
Yep, I can read it.
Okay. Okay, so this will simplify. Right, for one, right, we have to worry about this term, the mass term.
So
remember, what are our commutation relations? They say phi is 0, pi is 0, and it's only phi that's non-zero, right? So for stuff involving phi, I probably shouldn't worry. It's not, I guess, so obvious because it's phi squared. But let's remember a helpful trick for commutators. So I think I wrote down the. It's easy to derive, but let me just write it. So if you have things like a p squared. Remember, there's a good way to makes this easy. Let's be the other side, maybe. So you could check if you wrote it out that, of course, since I have two commutators, there are really four terms, but one has a plus and one has a minus for two of those, so they cancel. So that I have four terms secretly, but they become two, right? So you could use this. So let's look at, say, the last term. I have phi squared. I mean, really, this is x, phi evaluated at x, and this is phi evaluated at y. But I don't have to keep track of this because it's a phi thing, right? Because there's no delta function anyway. It's 0 always. So anyway, this would be phi comma phi plus phi, right? So that's 0. This is 0. That's 0. So mass term, I don't need to worry about. So what about the gradient term? Let's write that down. Right. Right, sorry, let's look at the first term. So that has things like, well, it's phi squared, right? Really, pi x, pi y squared. So by our nice commutator rule, right, this would be phi x comma pi y, phi x plus phi x, phi x pi y. So, and these are the same thing, right? This should be I delta 3 x minus y. And that's a delta function, so it could be on the left or the right of phi x. So these are the same term, right? So this whole thing is 2i d3x minus y on phi. Oh, sorry. Yeah.
Phi y.
Sorry. I was imagining a term that doesn't exist. Right. Be pi y. This is pi of y. Right. So the other, right, d phi, we also don't have to worry about it. It depends only on phi stuff. So in the end, our time dependence of phi will only have And right, remember, right, in doing this step, we've done the commutator, right? So now on the right-hand side, there's no more square brackets and commas, right? Is that clear because of this step? And now we've done all the commutator business. We still have a dummy integral. We have d3y, now 2I 3 minus y pi y. Right, and this is in Heisenberg independent time. So now we can just...
I got a quick question.
Oh yeah, sorry, there's also a half that I forgot about. Right? So when I did this step, I should really have this half from 1/2 pi squared. Yeah, sorry, what's your question?
How did we say that the middle term vanished, the gradient term?
Right, since it's going at stuff like phi and phi again,
Right.
so that will only at the end of the day be related to things like phi pi squared. I mean pi.
Okay, same argument.
Yeah, yeah. So the
Right.
the other,
Okay.
So next we'll also do d pi dt, and then we'll have to worry about the gradient and the mass term. So
Right, okay.
it'll be exactly balanced. If it's irrelevant for one of them, it'll be relevant for the other one. So everyone is equally relevant in the end. Okay, but is this step okay? Right, so now I have a half and a 2 and a delta function, which is just saying, forget about y now, right? Everything is really just x. So I get that this is, and I have an I or pi xt. So let's summarize, right? The end result for our Heisenberg equation of motion is d phi dt is just equal to pi. Right, because I had i's on both sides. So let's do the same thing for pi. So ddt pi x. So this will be, this is again pi comma h, right? We'll have the same big h term again. d3y. Oh, right. Let me just write it as pi y squared, same writing. 1/2 L5 y squared and 1/2 m squared phi y squared. Right? So now the term that was relevant for us is irrelevant. But now, in a sense, it becomes twice as bad, though, because we have 2 terms we have to worry about. So the gradient is the only one that's a little bit subtle, I guess. This, right, will be basically the equivalent of what the first term was doing in the previous case, right? But now we have a derivative, so it's a little confusing as to what's going on. The thing that we care about now, let me also suppress the space index. So the second term is looking like that, right? So with that same commutator rule, I can at least write something down. Pi d phi plus 2 phi pi but only y, right? This is a pi that depends only on x. So if I want, I can pull that guy out. I have pi x, pi y, and d phi y. And the same thing, that d phi y guy, and a derivative with respect to y acting on pi x phi y. So far, so good, right? So this is something I know, it's in the wrong order. It's usually we have phi comma pi. So since it's the wrong order, it gets a minus sign, and an I. And we'll still have this dy. But now the dy will be acting on a delta function. Times that d phi y, and plus an I d phi y, with the derivative again acting on a 3 delta function. Okay, right, so we don't bump into too many things. Right, is there... Oh yeah, sorry, I think there's a minus sign, because this is still the same thing, so this should also be with a minus sign, right? So they're the same term, again. We'll have a 2. And secretly this term has a 1/2 in front of it, right? So same sort of cancellations happen like before. Minus 2i. Derivative on the delta function. And d phi y. Right. The last term we can do. Very straightforward. Yeah, the last term, yes. Last term is really smaller than something we had. So this is phi phi phi, phi phi phi. So in the end, this is with a, oh, I think, oh yeah, with the wrong sign. This should again be with a minus sign, right? You don't have, yeah. Minus 2i, d phi d3, x minus y. This is really basically the same as what we had when we were looking at d phi d2. Okay, so our equation of motion has this form. Right, now, right, again, the thing to emphasize is now there's no more brackets. Now the commutators are all evaluated. And we do have one dummy variable integral to do, which is over this thing. This one's trivial. We could do that very easily. But derivative on a 3 delta function is a little funny, but we can evaluate that too by integrating by parts. If I want to save that stuff. So we have a minus I. Right, so the 2's and 1/2's cancel, so there's just minus i's everywhere. Delta phi, sorry, derivative squared, so y. And this times by y, that whole integral, and just plus, so it's really this term plus the m squared phi squared. Oh, sorry, m squared phi, right? right? And the final thing to do is to integrate by parts, which is equivalent to basically moving this derivative over to this side. That's really what you do when you're doing integration by parts. Right? You're flipping a derivative from acting on one part of the function to being on the other part, and then you have this, the uv term or whatever, the part that's a non-integral part. But that part is like the surface term, which will vanish for us. So I'll suppress some of the stuff, but yields then that for d pi dt, you get that term becomes just a del squared phi and minus. So this guy also should have an I, right?
Minus.
With a minus. So still, by the way, right, let's not forget what was the point of doing this. What the point of doing this was that we want to make sure that we haven't secretly violated Lorentz invariance. Because these pictures, Schrodinger and Heisenberg, seem to pick out time as being kind of special. Both of them do, in different ways. Let's compare this with the one we just found, which was d phi dt phi. We found these as sort of being core equations of motion that we have to worry about, right? In the Heisenberg picture. In the Heisenberg picture, yeah, we can get all the equation, all the time dependence just from the commutator that we just evaluated. Let me call this equation 1 and equation 2. So if we like, right, we can just stick equation 1 into equation 2. It's just fine. Let me forget about pi. Just put what the definition of pi is into equation 2. So if you insert 1 into 2, what do you get? So we get d squared dt of phi is del squared minus m squared phi, which hopefully looks familiar, right? This is now something which I know how to make sense of. This is the same thing that I can write in an explicitly Lorentz invariant way. This is a Klein-Gordon equation. Right? This is exactly the same thing as that. I can move everyone to the left-hand side. Space and time are acting the same, except one has a minus sign, like they're supposed to. Now, instead of minus m squared, we get plus m squared. So this is the Klein-Gordon equation, right? So all of a sudden, at the end, at least we see that Lorentz invariance was not violated. It's explicitly
Del
Lorentz
square
invariant.
pi
What?
over del t square.
Oh yeah, thanks. That's right. Right. I mean, that makes sense because we have two time derivatives, right? Just plugging that in. Okay, so things are reasonable in explicitly Lorentz invariant. So, right. By the way, just as a so these equations really don't look super Lorentz invariant, but they are. So when you find an equation like this, though, that you can write in a nice way with indices and everything, where it's obviously Lorentz invariant, people call this manifestly Lorentz invariant. You don't have to check anything because it's already has stuff that are, by our definition of our notation, Lorentz invariant quantities, right? So that's why it's nice to work with things like this. But this isn't obviously quantum mechanical either, right? This is the same as the classical equation of motion. So there's this funny tension, right, between quantum mechanics and Lorentz invariance. Did you have a question? Right, so the other nice thing we can do further with this in the Heisenberg picture is write our Fourier expansion in a way that's manifestly Lorentz invariant. Because before, right, we had we're doing had only spatial stuff in the Fourier part, right? When we do our Fourier expansion, it's all e to the I px stuff, and the p and the x are just 3 vectors, right? So that's also not explicitly Lorentz invariant. So let's see what that looks like in the Heisenberg picture. Right. We can also check that our Fourier expansion is Lorentz invariant. So first, to do that, let's look at what do the annihilation and creation operators look like as they as they change in time. So, right, by definition, the way that this operator should look as we go in time, right, is just given by how we define things in the Heisenberg picture. So I should be e to the I, ht, time-independent operator, or the one that we use in the Schrödinger picture, n times e to the minus iht. So something you can show as a consequence of the commutator relationship between A and H is that this is just equal to e to the I e, which depends on the momentum, t, and I get back to the same thing. So this follows from the nice commutation relations that h comma a is minus ep ap. And similarly for the creation operator. So we have AP dagger time-dependent, just, oh sorry, I think I switched to the minus sign. So this is the one that gets the plus sign, I, EPC, AP dagger. So we won't check that this follows because we have a lot of other things we have to do too. But right, you could see a way to do it just with basically sort of perturbatively, right? If you did some Taylor expansion of the exponents here, gives you a way of writing down what the right-hand side of that equation is in terms of A's and H's acting on each other. So, but with that definition, now we can absorb the time dependence, right? So what we're saying is now, let's go back to our old Fourier expansion, but now I have to worry about time dependence of that guy who's appearing in the Fourier expansion, right? And now he comes with the e to the I pt, which is great actually because he could be friends with the e to the I px, right? We'll match up space-time part, or sorry, xp part, so space and momentum part with a time energy thing. They'll appear with nice opposite signs, which means we can just redefine it as being a 4-vector inner product. So now the Fourier expansion in terms of annihilation and creation operator. And now, right, the crucial thing is now that guy depends on space and time. So, sounds okay. And d3p over 2 pi cubed. We have this 1 over square root of 2p. We didn't really talk about it, I don't think, but we'll get to that in just a minute. And now the annihilation operator with the e to the minus p dot x and creation e to the I px. Or really what that thing is right, this is at least now, again, just like the nice version we like for the Klein-Gordon equation, which just says mu's and stuff on them, this is something that's explicitly Lorentz invariant. The integrand too, I don't think we talked about that. This integrand, it's by itself Lorentz invariant. So we'll talk about that just now too. And so you can also check and verify that it satisfies the Klein-Gordon equation also.
Is there no t in the exponent?
Oh, so sorry, I should make that more. So this
Oh, yeah,
limits,
yeah.
yeah,
Sorry.
yeah.
Yep.
So p mu was dp comma p.
Great.
Yeah. So that was the step. So I just took our old Fourier expansion, right, which had a e to the I px, and now everywhere there's an e to the I px, he comes with the e to the minus I pt. And the minus sign is crucial because it means it's really in the right form to be a Lorentz invariant inner product. So I could just rewrite that as a mu lower, mu upper type of thing, right? So this also sets us up to start talking too about more about the relativistic normalizations that we choose. Are there any questions about what we did? All right. So, right, remember we were looking at the inner product between momentum eigenstates. We found it had sort of a funny normalization to be Lorentz invariant. That had some other consequences related to a few other things. So, more on relativistic normalizations. So I think it was last time that we found that the inner product between among momentum eigenstates is not the thing we have in the good old-fashioned low energy world, which is just a delta function, but a delta function that comes with EP. The 2 is really a choice. Right, remember we found this when we were looking at the momentum eigenstates. So, related sort of normalization is a Lorentz invariant integration measure. Which is d3p over 2ep. So that thing really is Lorentz invariant. So let's see how we would get that. That's not super clear right off the bat. So let's start with something more straightforward, like Lorentz invariant. It does seem funny, right? And also when I was writing this, these things are nice, and obviously Lorentz invariant, because it's just a x mu, p mu. This is less nice, because I have singled out spatial momentum and energy. But that doesn't mean it's wrong, it's just sort of funny. Maybe it's Lorentz invariant. If things had been before P, probably no one would complain, right? This seems obviously Lorentz invariant, right? You're treating everyone the same. So this is Lorentz invariant by I, right? Lorentz invariant. So let's start out with that, and we'll be able to find out that this is secretly the same thing. So right, we can also, the other thing I know is obviously Lorentz invariant is what we'll use is the dispersion for our particle mass m. Is mu is m squared. Right, this was just our way of writing down that energy momentum invariant. So what does this mean though? So this means I guess we were writing it as, if I read it as the 4 vector, I read it as P naught squared minus P squared. Right, the funny thing is, right, I've singled out energy, so let me remind myself how I get energy from this more obviously Lorentz invariant thing. So energy, which is the zeroth component of my 4 vector, is some square root of m squared plus p squared. And right, the sort of unfortunate thing is I have to pick a sign when I do that. Lorentz invariant doesn't tell me which one. So I have 2 branches, but that's also a Lorentz invariant choice. If you pick one branch, you stick on that branch. So you have to pick one of those branches. Let's pick the positive one. So also, right, this should be so this measure should also be Lorentz invariant. Let me do a D4 dP where I impose the correct dispersion and the right into one branch. I'll have impose the delta function P naught squared minus m squared minus p squared, and stick with the P naught being positive. That thing's also Lorentz invariant. And we encountered a delta function similar to this before. Remember, it's not, you can't just use the straight definition of what the delta function does here because it's not delta function of x minus x naught or something. We have to use that funny theorem, which was that delta of f of x is 1 over the derivative of the function, and that will give me delta x. So the thing that's like f here is now this function. So now if I integrate over, if I do the energy integral, right, which will impose the correct dispersion, the thing that will give me, right, is a 2EP, 2 times P naught, basically, because of that derivative, right? Which is exactly the thing I want. So it turns I'm just doing one of those integrals, right, just the energy integral. So I'll still have the D3P, but now I impose the correct dispersion, and I'll get that funny 1 over f prime thing. So this gives me that if that thing is Lorentz invariant, like we just argued, then so is D3P for 2P naught, with P naught being equal to positive EP. So that's good. So this also verifies that, well, we'll use this integration measure many times. It also verifies, though, that the previous Fourier expansion we just looked at in the Heisenberg picture, all the pieces of it are Lorentz invariant, right? That measure that appears in the prefactor, and also the exponents in that are attached to the annihilation and creation operators are. Right, this is also a good check on our normalization. Right? So remember, this was the normalization we chose for the 3-vector eigenspace of momentum, right? So it's also a good check on our normalization. For these 3 vectors, because I want to do the integrate over all possible momentum energy relations I can have on that inner product. I should get back just the same state, right? This is sort of related to the resolution of identity also. This is all obviously as well. So we properly normalize things. So this also tells me, remember what resolution of identity was in quantum mechanics and non-relativistic quantum mechanics? Or the completeness relation, we called it by 2 different names.
Sum of all basis vectors spans the space.
Yeah, exactly. So if you are summing over all the basis vectors, and they really span everything, then, right, this is another way of resolving one. So we call this resolution of identity or completeness relation. So in non-relativistic quantum mechanics, it was 1 is just equal to this. So it's saying if these i's are a complete basis of states, right, I can always expand any vector on that basis, and everything's fine. I don't lose some information about the state, right? So this is just saying the same thing as saying I can expand psi in this way, right? So this is the shadow cast by psi in the ith direction, right? And that tells me how much of the I vector he gets to have the full state, right? So since I can always do this, that just means that this thing is 1, right? So that was resolution of identity. So this is all of our previous normalizations and so our Lorentz invariant normalizations. Imply can have a resolution of at least single particle states. So, meaning, at least when I'm doing this expansion, I'm not including possible 2, 3, etc. particle states. I'm just sticking to the old-fashioned non-relativistic quantum mechanics world where I just have single particles. That's T3P over 2 pi cubed, P, and 1 over 2 PP with a P. So you could check that, using this relationship, for example, that this indeed is the correct thing to do for the resolution of identity. Check by applying to Q, for example. Okay, so a lot of stuff about normalizations. We can use it to build up some more of our intuition, though, on how this is connected to non-relativistic quantum mechanics. So any questions about this? Just sort of mostly reviewing old ideas in this slightly new language. So, finally some physics, instead of just making sure we're not doing something crazy, just making sure things are Lorentz invariant and have consistent normalizations. So let's interpret the state of phi acting on the vacuum. So now I'm going to stay with the Schrodinger picture, our old way of doing it. So I'll look at the old expansion. Yeah. So let's remember what that Fourier expansion looked like. Annihilation, IPX, and creation into minus IPX. And we had our, remember what it would A and A vector do on 0? What's A on 0?
0.
0 by definition, right? That's what we meant for any P, doesn't matter. And what's a dagger on 0? So we had to fix the right normalization, but this by definition adds amount P, an amount of momentum P, right? So this is momentum magnitude, a single particle, momentum magnitude, right? And we chose this normalization. Right, so that means, right, this phi acting on the vacuum state, that simplifies a lot, right? I kill one of the states, or one of the terms. So this is d3p, 2 pi cubed, 1 over, right? And I have the same square root of 2e's. And the exponent, and now just that momentum eigenstates guy, the e to the I p x. So this actually should be familiar, except for this funny part. If I didn't have that funny part, what does this look like?
Transform to the x basis.
Yeah, exactly. Right, this is saying that this is just a linear superposition of momentum eigenstates. So it looks very familiar to the thing like position eigenstate in non-relativistic quantum mechanics. To this X state in non-relativistic quantum mechanics. Right, except for the 2EP denominator. But, right, let's remember what we were effectively doing in non-relativistic quantum mechanics. In this, relativistic quantum way of thinking about things, we should only sort of get back non-relativistic quantum mechanics at low energies, right? Definitely below things like pair production threshold, right, where we have only a single particle and things are well defined, in that limit where things can map on to non-relativistic quantum mechanics, this thing is basically constant, right? E is something to do with mass and something to do with momentum. So effectively we're looking at low momentum, which just means this is just a constant thing. It's just something to do with the mass, basically, right? Roughly speaking. So really it seems like it does make sense that this is going to map onto something like a position eigenstate. It's very, very similar at least. So, right, because of that similarity, right, and also since the only difference is 2 EP thing, it's basically a constant at low E, we could put forward the interpretation that phi creates a particle at x. Right? It looks very much like a position eigenstate sort of thing. We started out with nothing. We started out with the vacuum. Right? So we'll put forward, since we have this low energy thing, we'll say that phi acting on that creates a particle. At x. But this is sort of further confirmed by looking at what happens if I project that on, if I project this state onto a momentum eigenstate. So if I look at something like 0 by x acting on p, this is going to be proportional to the e to the I px. So instead of the minus, it's a plus because I'm putting this guy on the left, he becomes the rod. Anyway, but this is similar to what happens when we looked at projection of x on p in non-relativistic quantum. Right? This is look like the wave function. This state is really looking like a non-relativistic quantum mechanic wave function. So we can also go further and show how the Klein-Gordon equation at low energies maps onto the Schrodinger equation. But we're not going to do that yet. We'll come back to that a little bit later. Okay, any questions about this? So mostly we were talking about formalism and definitions, but I think also we're building up a little bit of our intuition about what these fields are and how they connect with what we knew previously. Okay, so since we have a little bit of time, let me start talking about contour integrals. So the thing we want to do is next move on to propagators. Talk about how field value at one point in space-time is correlated with the field at another part of space-time. And this is ultimately related to the fact that when we try to compute that at the outset, right, we found something that was not causal, not proper in the sense of special relativity. Not causal because it would allow things like you communicate with things outside your light cone. So the integrals we'll write down look at how the propagator really works in quantum field theory. Those are sort of challenging integrals, and the best way to evaluate it is with this technique. So let me start talking about Those either notes on complex contour integrals. So how many people have seen this sort of topic before? Things like the residue theorem, Cauchy's theorem, yeah. Okay, so some people have. Where did you encounter it? Just like in a physics class?
No, it was in a math class.
In a math class, yeah. So this is,
Mathematical physics.
or in mathematical physics, yeah, yeah. So right, so since it's not something that you can assume everyone knows, we'll spend just basically one lecture or so talking about it, which will just start now. We won't get finished, but so one thing you might want to do, maybe I should even assign this as homework, but you might want to read up on contour integrals. Either just at something like Wikipedia or this book, Brown and Churchill. That's the one that I like, that's really pedagogical. So it's just called something generic, like complex variables. So I don't want to spend too much time on this. I'll really try to just limit it to one lecture. But it'll be really helpful for going forward. And also, right, you learn a new way to do an integral that in some cases you wouldn't be able to do the integral any other way. Even if, and this is the powerful thing, right, even if you don't care about it being complex, even if you really are secretly just interested in a real integral, promoting that integral to something in the complex plane gives you some powerful theorems to take advantage of. Right, so I'd really recommend that book. Okay, so what we'll do, right, so let's take a 2D plane. So probably you know sort of how to do normal contour integrals, things in just normal Cartesian coordinates. But the difference is, right, this isn't just any old XY plane, it's going to be the complex plane. The complex plane, parameterized by some guy called Z, who always appears in this way, right? That you connect X and Y with an I thrown in there, right? So that's the special thing about doing integrals on a complex plane. So the thing we'll be interested in are study objects like this, so some integral over some function evaluated along a contour. So this thing, where C is a contour in the complex plane. And the reason that we can take advantage of some powerful things is that this f of z, right, he's not a function of some arbitrary combination of x and y. He's going to be what's called analytic. So the crucial part is that it's going to depend only on z, again with this x plus I, y thing. It couldn't be that I consider functions that are just something like x squared. It has to be only depending on z. So these are called, we're not going to define it precisely, this is really a physicist's introduction to this topic. So we'll call these analytic functions. So if your function is analytic, which roughly speaking means depends on z and not z star, not as a complex conjugate, then you can apply some really powerful techniques. You also need to have a derivative well-defined within the contour. Right, but the neat thing is that if f starts to be singular anywhere in the complex plane, anywhere within that contour, then the result can become very, very simple. We're not going to prove the theorem either. That's a math thing, and I'd recommend checking out that book if you want to look at it further, or just Wikipedia or Wolfram page about every math topic. But so right, let's suppose we have a pole. That c equals z naught. So then we'll write this analytic function as being something like some number, some constant over z minus z naught. So right at the value of z equals z naught, that thing explodes. And you could have some extra piece that's regular, that's non-singular. So this is some non-singular function. And this thing we call the resident. So just the prefactor in front of the 1 over diverging term. So to start with, right, we'll just consider functions that have this kind of pole. You could have different poles, right? You could have this quantity squared in the denominator or something else. But for this first simple type of pole, an incredible theorem applies. It's called Cauchy's residue theorem. Which says that you do that interval over nearly any contour, as long as that contour encompasses this singular point, the result is going to be 2 pi I times the function evaluated at the pole. So you can see why that's very powerful, right? And pretty general about C. Mostly I just want to make sure C doesn't go through some diverging part of the function or something like that, where the function becomes ill-defined. But as long as that doesn't happen, I can evaluate the integral in this really simple way, without doing any work, basically. So this is the trick that we'll use in physics a lot, is we'll arrange our contour. Mostly we're going to care about integrating over momentum, something like that, something real, right? Like when we do that, right, we could always promote the momentum of some complex variable, draw some contour that is along the real axis. So part of the contour will be the thing that we care about. The other part will be able to, most of the time, send to 0 or do some nice arguments so we can forget about the other part of the contour and get out what the result is right away. And there are some integrals, so I want to go over some cases where you can get back results that you already know are correct. Get back integrals you already know. And we'll also be able to do integrals which I don't know how to do otherwise. It's very nice. So let me stop there and we'll come back to this next week. And shortly after that, see why we're doing propagators. Any questions?
Is it f at z over z minus z naught? Or is it just f at z?
So what I'm doing here is separating out the pole part.
Oh, okay.
Yeah. So there's also more elaborate this is only really for the simplest type of pulse. We'll talk about also what happens if you have
Okay.
yeah, different types of divergences. But I wanted to start with this simple
Yeah.
first. Yeah. We'll upgrade pretty shortly though. All right, so don't forget about your homework. So email that by the end of the day. They'll assign a new one pretty soon.
Are you heading straight home or you want to go grab something?
I gotta head straight home. I gotta meet my kids at 1:15.
Yeah.
My schedule's really tight this semester. I taught my first class yesterday.
How's that?
Yeah.
How big's the class?
Different 30 students.
Not like a huge thing, but like.
No. Yeah. But it's a little hard because it's long like this. Like it's an hour and 20 minutes. Felt like they were pretty bored by the end.
Are you gonna try that? Yeah. Is this the first time trying that? Yeah, it was okay.
I wrote mostly second person.
Oh, I see. Yeah, yeah. So you're doing hybrid
That's right.
sort of slides, but also yeah. I see.
Have to face the question.
Yeah, yeah, yeah. I see. Cool.
Yeah. If you have a PDF version of this one,
Uh huh.
you can just.
That's true. That's true. There's a lot of equations that don't show that too.
Yes, I know.
Yeah, yeah. All right. Well, good luck.
Nó lâu hẳn đời làm sao?
You can also read the slide or just. So if you check the D to L, so there is conflicts. The first one is green. So if you click on them, you can
Yeah,
you can,
I,
you can
I,
watch
I
it.
already saw that. I did. Thanks.
The last doing a meeting. Yeah.
Iya, udah pulang. Dari kota Timur. Sampai